Hello, my name is Wittenberg and I'm a PhD student at the Chair for High Performance Computing of the Hammersmith University, Hamburg. And today I'm going to present to you my latest research, which is a sensitivity study on transient two-way molecular continuum coupling with OpenFOAM and Numerics. My outline for today is first I'm going to explain to you why we would couple molecular and dynamic simulation with continuum simulations. Then I'm going to present my setup for the two-way coupled simulation for QuadFlow, give you my results on the sensitivity of coupling parameters, and finish with a summary. So, molecular dynamic simulation, short MD. They model the physical movement of particles. This includes interparticular forces, which are calculated based on particle pairs. So iterating through every particle pair within the domain gives a huge number of calculations and operations, and thereby MD simulations are going to be computationally really expensive. Anyway, people want to use them for research and development, and so there's a way needed to get them cheaper. And what people usually do is to minimize the size of the molecular dynamic domain and just use it where high resolution data is really necessary. The other parts of the domain will be simulated with a coarser continuum model. For example, one could use here a Lattice-Boltzmann solver or a Navier-Stokes solver. This approach is called a molecular continuum model. In research, there are already several people succeeded in doing this, but usually they are using one setup, and when they go to another, they don't really talk about how they change parameters or even set parameters. And when one wants to reproduce the setup they did, it's really hard because there are so many parameters and the simulations are really sensitive when they are not set in the correct way. Therefore, a deep understanding of the parameters and their influence is necessary. And that's what I researched in, and I'm going to present to you today. But first, I want to present my setup, which is consisting of three parts. First, we have simple MD, which is the molecular dynamic model. It's a linked cell-based molecular dynamic code. It simulates Lennard-Jones particles. Then I use Ecoform, which is part of the OpenFOAM library. It's a finite difference solver. It works for laminar flows. It's transient and incompressible. For the coupling, I use Micro, the micro coupling tool. It's developed for coupling arbitrary molecular dynamic with arbitrary continuum solvers. And the goal is to have a high performance and to work in highly parallel. It has some further functionalities, like you can use multi-instance sampling, filtering, data analytics. The grid in my setup, or the domain, is split into two parts. So we have on the left down picture, you can see the outer yellow domain is the continuum solver, and the inner red domain is the molecular dynamic domain. Between both domains, we have an overlap of 3 cells. And the continuum solver uses a cubic mesh. Here I want to just give to you a little insight into the process of the coupled simulation. Due to the time, I won't go into detail, but the important point here is Numerics is in control of the simulation, so Numerics will trigger Ecoform or simple MD to do something or to send, and it will send and collect the data, but both of them will never communicate directly. Okay, so let's move on to the results. Therefore, I'm first going to present some parameters which influence the result from the coupled simulations. There is the cell size of the continuum solver. Since we have to sample the data from the particles to send it to the continuum, we have to use the particles and get one value out of it. And thereby, if we have a bigger cell, we will use more particles and thereby get smoother values. So smoother always means, or usually means, also better results. The flow velocity also influences decoupling due to compressibility effects, as well as when you use in the molecular dynamic model insertion or removal of mass, like you want to model flow over the boundary of the molecular dynamic domain. You insert remove mass, which is technically a bit difficult, and people usually, or the way it is done, it usually introduces little physical incorrectnesses and thereby introduces little errors, which then have an influence on the result as well. For the insertion of momentum, one can decide on the size of the region. You can use one cell layer from the continuum or two. When you just use one, of course, you have less information, you kind of lose information, and then the result isn't as good as when you use two. The last point I want to state here is the multi-instance sampling, what we do, because the fluctuations in the molecular dynamic are quite high. You usually use couple more than one molecular dynamic simulation with one continuum solver and then sample from the multiple instances, and thereby you can get again more smooth data and improve your result. Okay, so let's really come to the details. Here I present 9 results from 9 simulations. In the last column, you can see the root mean squared error. These simulations I did were a quad flow startup, and I compared the analytical solution with the simulated result and thereby calculated the root mean squared error and used it to check if the result is good or not. Okay, so simulation 0 is my baseline simulation, so I would call it a good, or I would name it a good simulation. It uses 200 instances in a multi-instance sampling. The time step is 2.5. I use a wall velocity of 0.5. For momentum insertion, the second and third cell layer is used. That's the 2 layers most close to the molecular dynamic domain. The boundary condition is periodic. There's no particle insertion or removal, and root mean squared error, it's quite low, as I would say. From now on, I will usually change one parameter so we can see the influence of this parameter. So, and at first I would use the numbers of molecular dynamic instances, and as you can see, the error goes up by a factor of 2, which is due to the fluctuations, as I said. When as in the second and third simulation, increasing the time step or the wall velocity, we will have a bigger difference in the time gradient, or we will have a bigger time gradient, and thereby the error also increases. As I already stated, the momentum insertion layer one uses is really important, and here I showed to you what happens when you use only one cell, but you can also choose different cells from the overlap. So cell 1 refers to the most outer cell. When you use the most outer cell, you get a quite big error compared to the others. And when you go more to the inner of the molecular dynamic domain, the error reduces. The last simulation I want to show to you here is one using mass insertion and removal. I don't want to go into detail how it works, but just again, it also introduces an error, but the error here, it's okay compared to the baseline simulation, I would say. But still, I think one should be aware of introducing an error by doing this. Okay, there we are already at the end. So just to give you a little summary, I just showed to you or gave you a little insight into the technical parameters of a molecular continuum simulation and what effect do they have on the result of the simulation, and therefore I examined the long-term behavior after 1000 MD time steps. what I want to do in the future is to go even further in the long-term behavior. Also, I want to evaluate a different flow behavior and see how the parameters influence this, if the effect is the same. And I want to check on a compressible continuum solver. And also we have one person in our group that is researching in a systematic error estimation. Yeah, so thank you for your attention. And I would like to hand on to Fran.
Thank you, Helen. Shall we allow for some questions, please? I don't have any questions in the chat, so I would like to thank you for your talk. And can you just say a few words about what applications you would need to do this approach for?
There is different cases. I mean, if people are researching in behavior of fluids, like in the detailed physical setup parameters, or also sometimes it's hard to get the correct behavior at the wall, close to the wall. It's also good to use coupled molecular continuum simulations, or in the research of when you have a polymer in your fluid, it's also good to use a molecular continuum simulation.
Thank you very much. I think Fran has got a question for you. So Fran, can you go ahead, please?
Sure, thank you. The question is in the chat, but I can read it out. Very nice hybrid atomistic continuum approach. The coupling at the overlap region is critical. What coupling equations do you devise for momentum and temperature? On the MD side, you typically have a thermostat. Which one do you use?
Wow, okay, that was too fast for me. I need to read it again, sorry. I will open it. Okay, so actually coupling equations are a bit more difficult. We basically use the same approach as the paper from me, which I quoted. So yeah, you can have a look there. For the temperature, it's just we use an we just apply a constant temperature, so we don't need any equation therefore. And yeah, we have a thermostat, as you said, and wow, that's actually much or deep into detail. At the moment, I don't know. I could look it up. I can send you the equation and also the name of the thermostat.
Thank you very much, Helen. Applause from my side. And let's move to our next presenter. The next presenter is Fran Delic, and he will be talking on the performance of the Schneider and Sauer cavitation model with discussion of conditions relevant for lubrication. Over to you, Fran.
Thank you, Professor Jacek. Hopefully you can hear me and see me well. Again, my name is Fran Delic from the Center of Scientific Computing at the University of Cambridge, and today I'll be discussing the work done from a master thesis titled The Performance of the Schneider-Sauer cavitation model with a discussion of conditions relevant for lubrication. So firstly, I'd like to go over the motivation behind this work. Next, I'll give my goals and the approach used for multi-phase modeling. I'll talk about cavitation around hydrofoils as well as cavitation for lubrication applications. And finally, I'll give my conclusion and suggestions or ideas for future work. So the motivation behind this work is quite clear. Cavitation itself is a limiting factor on many engineering devices and must be accounted for during the design process. For instance, the maximum velocity of America's Cup sailboats is determined by the onset of cavitation on the hydrofoil. As well as change the lift and drag properties of the hydrofoils, cavitation induces noise, vibrations, and wear. In lubricants, the distribution of pressure changes the load bearing capabilities. It induces additional phenomena such as suction lubrication, and it causes wear, which turns out to be the most important part for both producers of lubricants and lubricated surfaces. So how does wear due to cavitation actually occur? Here we can see a simulation done as part of my coursework for the MPhil. This is the collapse of a helium bubble in air. And if this bubble collapses near a surface, it can cause damage. The high velocity jet shown in the red arrows impacts the surface and causes deterioration. If we have enough bubbles doing that for a long enough time, something like this happens. So this is a propeller of a ship where we can see the damage done by cavitation on the leading edge of the propeller. So what are my goals? Firstly, to examine the performance of the Schneider-Sauer cavitation model on a 2D representation of a hydrofoil. Then to derive a general model reduction procedure from 3D to 2D, and to apply the Schneider-Sauer model to able to more accurately calculate cavitation for lubrication applications. The multi-phase approach is an Euler, where we have two continua. We have one pressure equation, two velocity fields with interface drag terms. However, if we assume that the fluids are immiscible, we can collapse the two momentum equation into a single momentum equation, where we use the surface tension term to replace the interface lift drag terms. We need to introduce a phase fraction equation to know in which phase we are, and this method is called the volume of fluid method and is commonly used within OpenFOAM. So first, I'd like to talk about cavitation around hydrofoils. So this is the equation set for an incompressible and isothermal Newtonian fluid. Here we have two terms of interest. First one is the gradient of pressure in the momentum equation, which is derived in this way. And the next one is the mass source term in the continuity and phase fraction equations, for which we need a cavitation model, in this case, a Schneider-Sauer cavitation model. The model itself assumes a homogeneous dispersion of N0 initial bubble nuclei, which have an initial diameter of D0. It's based on a reduced Rayleigh-Placet equation, as seen in the middle of the slides, and this reduction accounts for 3% of an error once the diameter is 3 times larger than the initial diameter, which is quite good. And the source sink terms are calculated using the expressions below. Now, going on to the result, this is an ECA 009 truncated hydrofoil. This is the time-averaged fraction field, where the white is the liquid and the blue is the vapor. Here we can see cavitation on the leading edge and a small cavitating area on the trailing edge. Looking at the lift and drag coefficients, we can see the quasi-stationary nature of cavitation and the cavitating sheets which detach from the airfoil, hydrofoil. And the next few slides will be the pressure distribution along the core length. So here we see the experimental data in the black crosses. The blue and red dots represent non-cavitating cases, which show a significant discrepancy, meaning that we need to account for cavitation, obviously. The orange dots represent a laminar case, while the green dots represent a turbulent case. In this case, it's a K-omega SST model, which again shows that we need to account for turbulence when modeling cavitation. Now, the next two slides are a parametric study where we set the initial number of bubbles. We keep it constant, and we change the diameter of the bubbles, with red being the smallest diameter and blue being the largest. Here we can see the larger the bubbles, the larger the cavitating region, which makes sense. On the other hand, the bubble diameter is kept constant for this set of data, and we change the initial number of bubbles, with blue being the smallest number of bubbles, 10 to the 6th, and magenta being the largest, 10 to the 12th. Again, if we have more bubbles, the cavitating region is larger. So good, the model seems to work for lubrication, for cavitation of the hydrofoil. However, we would like to do cavitation in lubricants. The finite volume method is limited because the problem of cavitation is that the height of the film associated is in micrometers, and the area is in millimeters squared up to centimeters squared. Therefore, the finite volume method would produce high cell aspect ratios, which limits its usage. An alternative is the finite area method, divided by Tukovic, which is a general reduction of the three-dimensional finite volume methods to a two-dimensional form applicable to curve geometries. The classical approach is to use a Reynolds equation. However, within its derivation, specific velocity profiles are assumed and convective effects are ignored. And this forces the equation to use a simpler cavitation model based on a switch function. A reformulation is the finite area Navier-Stokes, which allows for the introduction of more complex cavitation and shear stress models in which we're interested. So how do we get to the equation set? We start with the Navier-Stokes equations and assume isothermal flow thermal effects can be gathered by introducing an energy equation. We assume that the fluid is Newtonian, which is true for some lubricants, but not for most of them. However, we can remedy this in the shear stress modeling. We assume laminar flow, which is true for high viscosity fluids such as lubricants. We can apply the boundary layer approximation, again, valid for small heights of the film. And we assume that the liquid and vapor phases are incompressible and immiscible. This immiscibility allows us to use the volume of fluid method. We can perform a height integration and apply boundary conditions to derive the following set of equations seen here. Three terms are of interest. First is the gradient of the product of height and pressure, which is split into a sum of two terms, where the gradient of height is assumed to be small, which is valid for most lubricated geometries. The next term is the shear stress terms in the momentum equation, which are modeled by assuming velocity profile, similar as in the Reynolds equation. And the third term of interest is the m dot term, which is the mass source term due to cavitation. The equations are assembled at the Pimple algorithm and solved using a segregated solver. And this is still work in progress since the cavitating model hasn't yet been introduced. So I'd like to go just over one case, one validation case, which is a slider with pockets. These pockets are introduced into sliders to induce cavitation. And an analytical solution was derived by Oliver et al., in which the pocket height determines the onset and range of the cavitated region. So looking at this graph, this is a pressure distribution along the slider length. We have two cases here. So the first case is the analytical solution presented with the with the black line. So the analytical solution by Oliver et al. The red dotted line represents a solution using the new implemented method, and the blue line represents the solution using the finite volume method. All three of them show good correlation. The green line represents results from Oliver et al. For different pocket heights in which cavitation occurs. And the orange dotted line represents my results for the same case without the cavitation model introduced. So hopefully once the cavitation model is introduced, the orange dotted line will match the green line. So what are the conclusions? A cavitation model correlates well with the experimental data for the two-dimensional hydrofoil case. The general reduction procedure from 3D to 2D is valid for the pressure velocity coupling and the shear stress model. This has been validated. And what I need to validate further is to see if the Schneer-Style model can be used within the finite area method for lubrication applications. Future work is to do a parametric study to determine the influence of initial nuclei number and size on load-bearing capabilities. Next, I can implement a modification into the Schneer-Style model to have separate bubble growth and collapse equations in the cavitation model. I can modify the cavitation model to account for different surface texturing. So highly textured surfaces would be a source to more initial bubbles. And the big question is, can microscopic scale results, as shown in the beginning of the presentation, be used to model wear? Thank you for your attention. My email is below if you have any questions, and the references are shown on the slide.
Thank you very much, Fran. Thank you for the nice presentation. I am still waiting for some questions in the live Q&A. So let me ask you one myself. Sure. Why did you pick this particular cavitation model?
So firstly, why it was picked, it has been used for a lot of applications, a lot of marine applications, such as propellers, hydrofoils. It's been well validated and well researched. So that gives us a basis on which we can expand. And next, it has two parameters, the initial diameter and initial number of bubbles, with which we can introduce, let's say, a history of the fluid. So if the lubricant has been in a highly strenuous state, I guess, where a lot of bubbles are introduced, we can model that. And there are two additional source and sink terms within the model itself that we can further model to account for those things.
Okay, thank you. I have the second question in the chat saying, what is the Reynolds number, and do you need to use any turbulence models in your cavitation? And I assume that refers both to the two-dimensional airfoil and the gap model.
Sure. So I'm not sure about the Reynolds number. The velocity is 20 meters per second for the hydrofoil cases. I can look it up, but all the data is given in the PhD from DuPont. As for the lubrication, these results have been done across a range of Reynolds numbers. All of them are small because of the high viscosity and because of the low velocity. So the initial case setup for this is that the top wall is stationary and the bottom wall is moving. I think these results are 1 meters per second in this case.
Very much. Thank you everybody for the question. Let's move to our next presenter. Johannes Gansmann will speak about the study of the overset approach for simulating cycloidal rotors and a comparison with other rigid body mesh motion. Over to you, please.
All right, thank you very much. As you said, we're going to have a look at my topic that I continued from my bachelor's thesis on with my advisor. What we're going to have a look today at is, first of all, what is a cycloidal rotor? Next to it is what is overset. A specific function is the overset interpolation, and we're going to have a look at how this is working. What different mesh motion methods do we have? I'm going to present you a comparison of a single process simulation of these methods, as well as having a look at the overset OpenFOAM scaling capability. There is an issue resulting in pressure oscillations. We're going to have a look at that as well. And finally, we're going to have a conclusion and the acknowledgement. So first of all, let's have a look at the cycloidal rotors. As you can see here, we have two blades, and we can also inspect two different motions. First of all, one bigger rotation and the pitch of the blades. The resulting or the reasoning behind this is we want to have a lift because it's going to be a propulsion method for example, drones, UAVs, MAVs, especially smaller aircraft. The reasoning behind the cycloidal rotor is it's known to have very good stability and very good maneuverability, since you can change the direction of the resulting force instantaneously. Now, let's have a quick overview on what overset is. It's basically oversetting multiple meshes on top of each other. So for this example, we can see in the lower image, we have the background mesh. In the upper image, we can see the background mesh with a component mesh set on top of it. And this is the principle of overset. So you have independent meshes interacting with each other. There are two interpolations happening. So let's go through the color coding first. The red cells are whole cells, so there is nothing calculated. The blue cells are calculated regularly, as we know, and the gray cells are interpolated cells. So this is the transferring of information from one mesh to the other. And we can see on the topper image that the fringe of the component mesh has a ring of interpolated cells, and the background mesh has a ring of interpolated cells on the whole fringe. So there are two interpolations happening back and forth. That's kind of important to know. And this interpolation is happening for every time step. And with this coupling of meshes, we can create complex motions and have relative simple meshes. As you can see, I have just unstructured mesh. It's kind of easily done. Now, how did I create the background mesh, for example? As one important thing to know is that for the interpolation, the interpolated cells need to be similar size to the donor cells. So now we have the outer zone. It's pretty simple, coarse on the outside, a little bit finer on the inside. Now, the refined zone is a zone with cells that are all similar sized, and they're similar sized to the fringes of the blade meshes. So we always ensure that here we have similar sized cells. And the inner zone with the roughness regulation ring that I came up with is to ensure that we have enough information flowing through the center of rotation in order to see the interaction of the wake with the next blade. So we can see here only the red blade meshes are rotating around. Exactly. So this is a possible solution for a background mesh in order to have it run a cycloidal setup. Now, the overset interpolation, we can see here an example on the left side, inverse distance. It calculates the distances from each cell center to the acceptor cell. And like this, the value is weighted and then interpolated. We have different methods of interpolation. First of all, we've known inverse distance for now. There's tracking inverse distance, least squares, and cell volume weight for OpenFOAM ESI version. We're going to have a look at mainly at inverse distance and cell volume weight, because inverse distance is known to be the fastest and cell volume weight is known to be a bit slower, or the slowest in this list. So what mesh motion approaches are we going to have a look at? First of all, overset OpenFOAM ESI with the methods that we've just talked about before. The arbitrary mesh interface OpenFOAM AMI from OpenFOAM ESI version as well. Foam Extend has a similar version. It's called GGI, General Grid Interface, and Foam Extend also have a corresponding overset function with different interpolation methods. It's called injection and inverse distance. Injection meaning it just takes the value of one cell and just implements it into the acceptor cell. Now, I run a couple of simulations, 100 time steps with 500K cell size cells meshes. We can see here that AMI performs the best and the fastest, and GGI follows right after it, followed by Foam Extend overset. It's interesting to see that the injection doesn't saving a lot of time for the due to the interpolation compared to inverse distance, and follow the last winners of this race, so to say, is overset OpenFOAM with cell volume weight taking the longest significantly, and inverse distance following it up. So now let's have a look at OpenFOAM scaling from overset. The formula down on the right is a little bit difficult to understand because it's also German letters. So we have the efficiency, and it equals the number of processes, parallel processes that are used times the clock time that it took for the number of processes. So we have actually the combined time of every parallel process added up onto each other to see the efficiency. And we have as a benchmark, we have the clock time that was spent for a single process. So we can see how much time is actually lost due to the parallel interaction. We can see AMI is doing pretty well. It stays in the high percentages for very long. Overset decreases rapidly, and there's a small difference between the cell number of the simulations. So as you can see, 500K cells is a bit higher, but still these aren't good values, and it's interesting to see. Now let's have a look. Another issue that I talked about is the pressure oscillations that are happening. We can see on the left is OpenFOAM overset, on the right is AMI, and the pressure is quite inconsistent on the left side, whereas on the right side we can see it's very stable. This effect can be seen as well in the force in the forces that I've plotted here. The plots on the left side are purely overset, and you can see the lines are scattering very strongly. This is due to this pressure oscillation. On the right side, we can see AMI and GGI. They are very, they have a very sharp and clear line. So this is another issue that has to be considered with OpenFOAM, or maybe it can be even resolved. Now let's go to the conclusion for now. My conclusion is that OpenFOAM overset and Foam Extend overset, they tend to take a very long time. The interpolation takes too long. This can have multiple reasons. The first reason that I came up with is that the interpolation on the outer side of the fringe is going well because it's similar sized, but on the inner size, on the inner hole, we have the boundary cells. They're very, very, very small, and if you interpolate them, it takes a lot of time. So my former advisor and now boss Louis and me, we came up with the idea maybe to cut out a bigger hole. And my advisor Louis, he's working on it, and maybe if you want, you can have a look at it. I'm going to post this link into the discussion section, so you can look it up for yourself if you're interested. And yeah, another thing that I came up with is multimotion is needed. I didn't get it to run with foam extend. Bear with me, I'm not not the most experienced OpenFOAmer out there, so this is definitely a nice to have. So thank you very much for your attention. If you have questions, please ask them. I'm gonna open up a poll, so maybe you can give in your yeah, your field of work. If you have worked already with Overset, AMI, GGI, whatever, if you're interested in doing this, you can fill out this poll. Yes, so thank you very much, and back to you, Mr. Yazak.
Thank you very much. You have a million questions here, so let me just try and answer for as many as you can. So Martin Badouan is asking, would you consider publishing some of your cases so that we can take a look at the problems with performance limitations?
Yeah, very interesting. Yes, I could publish it. I just don't know in which way it would be the most sense. It would make the most sense.
For my personal reasons, we have the Ecoform project where we need to look at the efficiency of GGI and AMI. So you can either contact myself or Martin directly to look into that. So the second question is from Håkan Nilsson. He says there are interpolated cells both close to the blade, which are small to resolve the boundary layer, and at the edge of the overset mesh, which are much larger. Both of these must be interpolated from the respective mesh to the other mesh. Is it then possible to keep the interpolated cells of the same size? Do you have any recommendations of how to deal with this problem?
Yes, this is the issue that I've seen as well. A solution would be to increase the hole, to make it much bigger, so that the hole cutting and the interpolation ring cells of the ring of interpolated cells is further away from the boundary. So the cells are not going to be that small. So this would be an idea to maybe have a solution for overset to have a control on where the hole is being cut.
Joseph Naj is asking about the pressure oscillations. Did you check the convergence within a time step, and how many N correctors and N outer correctors did you use? Because sometimes that can make a difference.
Yes, for this situation, I use 3 N outer correctors. But yeah, maybe I have to play around. Maybe this can be resolved by making the case a little bit better. Yeah. So thank you very much for the tip.
Joel Guerrero is asking, is there a way to eliminate the pressure oscillations due to interpolation?
I'm not too sure if it's linked to the pressure oscillations. If the pressure oscillations are linked to the interpolation, but yeah, I don't know yet if it's linked to each other. So
if you'll ask me to continue with this, in the overset community, this issue of pressure oscillations has been known for 15 years. And apparently there is a paper somewhere out there which describes what needs to be done, because it is to do with the change of the volumes between the live and the blocked cells within the iterations. I have been desperately trying to find this paper for the last 5 years. So if anyone watching this recording has got it, please send it or put it on some forum.
Yes, my advisor and me, we would be very happy for this as well.
Okay, and the final question is from Jonathan Fellback, saying, when you talk about AMI, is it just regular solid body rotation with conventional dynamic mesh, or are you doing something else?
AMI is just a regular solid body rotation. We have the rotation of the entire blade, entire rotor, and we have the rotation of the inner blades separately in 2 pockets. So it has nothing to do with overset.
Thank you very much. I have a final question again, number 2, from Holger Marshall, saying, on GGI versus AMI, do you have any information on accuracy and conservation properties of the 2 surface interfaces compared to each other?
No, I haven't investigated on accuracy and conservation. Sorry. Yeah, it's more of a look into how fast they are. because we need to decide on which method we're going to use for our simulations.
Thank you for the interesting presentation, and thank you for answering a million questions. It was very nice. This is the last presentation in our session, and I would like to thank everybody for joining us. See you on a later session this afternoon. Bye-bye.